and with Professor Kourkoulis from National Technical University of Athens. You will allow me 2 slides with a presentation of I come from the University of the Aegean. University lies in the islands of the Aegean. This is my island, it's called Chios, very popular due to the refugees right now. And we traveled through Catania, through Athens. It was approximately 1,000 kilometers away. So I will motivate for my island. It lays to be the birthplace of ancient poet Homer, and it's very famous for this gum mastic tree that it's a resinous substance. And I will motivate again. It's a beautiful place to travel and have some holidays besides working in the university. Okay, now I will go to the presentation. I will first motivate myself, then explain the experimental procedure, present you the results, and if I'm quite fast, I will analyze them. The aluminium alloys still possess more than 60% of the per volume in the A380 Airbus, and right now 2024, though the oldest aluminium alloy is still used in the lower wing panel, and aluminum lithium alloys have already been established as a new alloy at the floor beams, and the trend is to change the 2024 alloy with the aluminum lithium alloys. So why aluminum lithium alloys? It has low density and higher modules of elasticity, and it has great damage tolerance capabilities. But today I'm going to speak only for quasi-static and properties, and try to explain a little bit about fracture toughness. So all these alloys are precipitate alloys. This means that with natural aging or artificial aging, the quasi-static properties are changing. For example, in 2024 you have theta prime particles, while in aluminum copper lithium alloys you have not one mechanism but 4 different. So it's a much more difficult situation. And why do we need these precipitates? Actually, they are blocking the dislocations. By blocking the dislocations, you increase the yield strength, but you sacrifice much on the ductility. So there is a trade-off between strength and ductility. So actually, we have motivated ourselves to compare the innovative alloy with the traditional one. So we perform the same artificial aging heat treatments, meaning that how in 3 or 4 years of natural aging, how they will respond to mechanical testing. So we perform tensile and fracture toughness tests, and then we will compare them. Okay, we have used the tensile test specimen, fracture toughness specimens according to the specifications, and we artificially aged here for one temperature at different times, and then we performed the tensile specimens were performed at a testing machine at NTUA. And we have used the typical CMOD and compliance method to evaluate K critical. So I will now move to the tensile test. This is for 2024. Here you can see artificial aging for increasing aging time. As you can see, the stress strain curves are changing, and for extreme overaging you have quite low yield strength and decreased ductility. And for extreme overaging, you have a recovery in tensile ductility. And these are the results for the 2198. After 3 hours, you have quite an increase in yield stress, 8 hours, 48 hours, up to again 900 hours. I will now move to the yield stress for different aging times. Here you can see this red line is for the 2024, so you can see that the peak aging is controlled with this peak aging regime. So you have an increase of 26% increase in yield stress, while the black one is for 2198. As you can see here, the peak for the 2024 you have very limited, so it's 20 up to 20 or to 65 hours, while for the peak aging regime, the innovative alloy goes from 8 hours up to 100 hours. So it's really impressive, and you have almost double increase in yield stress. That is really an advantage. Now I will move to UTS, where you can see that UTS is less affected by artificial aging. But the most critical one is ductility. Here you can see the red one is for 2024 and the black one is for the aluminum alloy for 2198, where you can see that you sacrifice ductility, more than 50% of ductility just to increase the yield stress. But bear in mind that yield stress is a design principle in aircraft charters. And here also you can see the strain hardening exponent that gives us more information about the mechanical behavior of this alloy. I will now move to the fracture toughness test and the results of the R curves. Here you can see this is 2024. You can see with increasing that aging time, the material becomes more compliant, which means that we expect a decrease in K critical values. And for 2198, for the same kind of specimens, we had higher values, so we expected higher K critical values. So with artificial aging, I'm sorry to disappoint you, but again we had a decrease in the peak of R curves, so that is continuously decreasing. So this is the summing up of the K critical according to ASTM standard, and here you can see you have at the peak aging regime you sacrifice almost 35% of K critical, while in the peak aging condition it's almost the same with aluminum lithium alloy. Of course we have some limitation due to the compact tension specimens, and as I noticed for a previous speaker with magnesium alloys, compact tension specimens do have some limitations regarding the K critical values that they can reach. So this is the typical graphs that they usually like, the aerospace engineers. This is the trade-off between elongation and fraction and yield stress, and this applies to the peak aging and the over-aging condition, meaning that the design engineer can actually select which is the most appropriate artificial aging to have a trade-off between tensile and yield stress and tensile ductility. And for example, the slopes that actually are marked here, actually you can see that 2024 gives you a higher or slower reaches the peak aging regimes. And here we also performed some fractography for the different aging conditions. Fractography is still under investigation, and we also see some dimples, and we have measured the dimple size that is increasing due to the precipitations. It's an ongoing investigation. So then I will conclude. The main thing that the innovative alloy has high potential in terms of increasing strength and not so large degradation in tensile ductility. Okay, we'll thank also Fokker for some investigation, and thank you very much all for the attention.
My topic will be a little bit different. I follow talk on bulk materials. I follow talk mostly aluminium, titanium, etc. We will discuss about coating, about fatigue on coatings, and mostly adhesion, because adhesion is one problem of fatigue too. And instead of discussing about plane, about welding, etc., we will discuss about coating for hard coating, mostly for application of cutting tools. And let's start with the motivation. Discuss about standards, analysis procedure, mechanical testing, physical analysis. My topic is really based on the physical understanding of materials and the coating test. First of all, designing coatings. You know, coatings are everywhere actually, and designing a coating it's really difficult, mostly because you have some temperature effect. Imagine if you have a cutting tool, so when you machine the cutting tools, what happens, you heat maybe up to few 900 to 1000 degrees, but it could be maybe few milliseconds. And having this type of temperature, it will affect the oxidation. You will change with the materials, with the geometry, with the naturally materials for the substrate, the chemical interaction, etc. Now, for us, a lot of people use scratch testing. From Untitled, we have a scratch tester, and most of people try to compare scratch testing, making a scratch. But it's not the real condition. We need to have a physical understanding of the scratch, of the mechanical property of the substrate in order to design a real test, simulating the reality. Naturally, everything is linked to return of investment, because if you can design and make some mathematics to define the modulus or the hardness of your substrate, your layers, etc., it will help you out. Naturally, all the talk is based on some standards. We have a standard for indentation because we will use a DLC coating of approximately 2 microns. So it means we need to use nano indentation. Nano indentation as a standard. Scratch testing, we have also a standard. We will discuss later why the standard is not always applicable. And we have a color test to measure the coating thickness of materials. What is interesting here, it's the new approach of the technique. Most of the time, people try to understand adhesion of materials, and they simply use the ISO standard. ISO standard tell you need to use a micro scratch test or macro scratch tester, use a tip of 200 micrometer of radius, you scratch from 1 to 100 Newton, and you check the delamination. But most of the time, the coating have changed a lot. Most of the time, the substrate are not anymore steel. We use hard metals, we use maybe titanium, we use sapphire substrate. And what happens, the stress involved in the mechanics of scratch testing are not the same, and it's difficult to standardize this type of test. It's why for this procedure, what we want to do, it's simply to start by an indentation of the layer. If you know the mechanical property of the layer, you can design a real scratch tester, making adhesion of coating and not fatigue or resistance on the deformation. First of all, we start with the sample. I tell you, we have a DLC, it's an ACH phase, and we want to know, the coating thickness. Using a color test, it's a fast machine, we can determine in few seconds what is the coating thickness. You see here the substrate, you see the top coating, and when we measure this scallop with different geometrical formula, we are able to determine the coating thickness of my DLC ACH is 2.85 micron. When I know my 2.85 micron, we know following the ISO standard and following the practice of nano indentation, you cannot surpass 10% of the film, because if you surpass 10% of the film, what happens? You will start to measure the hardness and elastic modulus of your coating with a substrate in front, what we don't want. We want the intrinsic property of the coating. It's why we do its 5 indentation overlay. You see, we define the max depth is 280 nanometer, and with the value here, I can tell you directly, we have an hardness of 25 gigapascal, and we have an elastic modulus of 216 gigapascal. Now, we start to develop and to measure the real stress, the real Hertzian stress inside the materials. First of all, to check if my indentation, I tell you it's 10% of max penetration, but we know 10% will work on almost all materials. But if you measure a copper coating, maybe you can go up to 40%. It's so plastic, we will not have any stress inside the substrate. At the opposite, we know the DLC start to have some influence in the substrate, and maybe the hardness is affected a little bit by the substrate, and in this case, you see, we have a small influence that it will be maybe nice to do 180 to 200 nanometer to check if we have any influence of the substrate. After the determination of the Hertzian stress inside the coating, we can design a real scratch tester. What is a scratch tester? You use a diamond tip, you apply a load, a constant progressive or incremental, and you move your sample. The idea of a scratch is really to make a small scratch to start to generate cracking and maybe adhesion problem of a coating. During the scratch, if you have a tip, you see here, making a, okay, it's a lot of deformation, but we try to have always some compressive stress before and tensile stress behind, in order to measure if it's cohesive or adhesive. What happened here? This one is following the ISO standard. You see here, we have a scratch tester, it's a standard software. You see from 0 Newton up to 60 Newton. What happened at this position? Here, we have an adhesive defect. We generate too much stress for the coating, and we cannot stress more. It means we delaminate the coating. What is interesting, we don't have the zoom, but from the LC1, we start to generate cracking. The cracking first are not a property of adhesion, it's simply a property. This one is the penetration depth of the tip during the test, and residual depth. I can tell you at this position, we have approximately 4 micrometers of penetration. My coating cannot deform with such penetration. It means we crack to unstress, but not by adhesion like this one. After you have a full delamination, but I think it's not really the topic here. What happened? We change now with a 100 micrometer tip in order to check the real condition, 50, 20, and 10. And what is very interesting here, if I come back on the first one, you see also the 100, on my residual depth, I see some noise when I start my delamination, when I remove the materials, but I'm not in a good regime to make adhesion. It means I'm not chipping the materials. Changing to a smaller tip, at this position you see I have the full delamination, the cohesive spallation. This one will be my coating thickness, because the regime with the stress is so high on this position, we chip completely the materials. You see as a comparison, it's not the same load, it's always the same length, 2 millimeter, but the type of crack are completely different. And changing the stress you induct inside the material, so we change from adhesive stress to deformation, I will say. This one is a resistance on deformation. After, naturally, what is interesting is to compare the 5 samples we generate, the 5 scratch we generate with the machine, to know where will be the max von VC stress. And here we have some reply. When you have, you see my 2 micrometer coating, you see my max von VC stress here is 4 micron. It means I'm not inside the coating to generate stress and cracking, but in the substrate. With 100, again, on the substrate. And more I change my materials, more I'm close to the interface, and it's why we have adhesion and not resistance of deformation. This one is another example, because I think it's very important. It's some DLC plus 1 titanium nitride. And what happened here, you see the titanium nitride, it's cohesive instead of adhesive. That's why we have this slide. And we can always compare them. But when you are doing real adhesion test. When you want to compare adhesive property of a coating, if you follow the ISO standard, meaning the 200 micrometer, you will have some difference between each materials. But when you start to customize your design, naturally you have less difference, and maybe the worst one following the ISO standard become the better adhesion at the end. It's really a question of stress inside the materials, and this stress will have some problem with that. Okay, naturally we can always analyze with to know the stress field, and the real idea of this approach of testing, it's instead of developing coatings or different materials, if you are able to use a software knowing the substrate property, 1 layer, 2 layer, 3 layer, 4 layer, 5 layer, 1 layer, you start to do some modelization before you do your test, it will be cheaper and you will have a better return of investment about the approach of developing the coating for fatigue, adhesion, mechanical property. In conclusion, a better understanding of the fire mechanism are very important, but by physics. The sensitivity of scratch test shows some coating substrate architecture, and we can increase the load range or inlet radius to simulate different stress. And the dimension can be supported by a software naturally, and it's easy to do. Thank you.